All right, recording is rolling. So Monday, January 23rd. So here's a top scientist for simple harmonic motion. Uh, so awesome job if you're on that list. All right, let me check my makeups. Some of you guys gotta make this thing up. Let me pause this real fast. All right, recorder resumed. All right, so good there. All right, so yeah, I've got the solutions ready to go. Just haven't posted them to the classroom yet. Once they're ready to take that, then of course I'll hand this back to you guys, and you guys can do correction of the whole thing. But yeah, that is it. Now we've officially covered all the AP topics. Yeah, so this semester is going to be mostly review. Every once in a while, I'll show you guys what's going on in my other classes. You guys, so many posters hanging up, but those for my honors and conceptual kids are going to move on to EM spectrum optics, that sort of thing. But, also got students got this UNICEF fundraiser. So let's see, what is this? Last all day, January 31st. So that's about a week from now on Tuesday, looks like. All right, if you go to Mr. Delicious Pizza, 3% profits going to UNICEF. All right. So yeah, I'm gonna scan this and put this on Google Classroom too. So got that there. Put this here. All right. Right, so I was going over the midterm solutions with you guys, which was a comprehensive review of everything in AP except for Unit 6, which you guys just did. Right, so we just got to hit these last couple. So I want to draw along with it for this one. We'll do that. We'll look at the Unit 1 guide from AP, just as a nice checklist. Right, so this next couple of weeks we're going to go back to the beginning, right? So Unit 1 by AP's book was kinematic motion. You guys remember that was linear motion and also projectiles, right? So I just opened up for you guys on AP Classroom a file called Kinematic 2. All right, I've got a due date is 1 week from now, Monday the 30th. That's tentative. That I might bump that, but at least for now, let's have that. All right, so yeah, I've got some extra AP Classroom files. And then, yeah, this one could be good independent study, and we might go over those possibly after you guys join that too, right? So it's just multiple choice questions. Maybe it's like 60 questions, something like that, multiple choice, right? So good practice for you guys. All right, so this week, I do want to fit in at least one, maybe more FRQs related to kinematic motion. So again, linear motion, projectiles, right? That's what you should be looking for. You guys can have a substitute on Thursday. There's like a professional development thing going on for teachers. Probably a lot of your classes will be like that Thursday. So I think I'll set you guys up with an FRQ. That's my plan right now. All right, and then I've got a kinematic review quiz for you guys. Now here, let me zoom in on this because we give you guys kind of an option, and then I can try to put my schedule around this. When you guys want to take this kinematic motion review quiz, it'll be a lot like the kinematic quiz you guys did last semester. Only, I mean, you guys know kinematic motion is something that you guys have seen over and over in physics because physics like builds, and you guys have seen like those 3 classic kinematic equations so many times. You probably have memorized by now, right? So here's some options. Maybe we'll do a vote and try to get this to a majority vote, right? So we could do this as early as 1 week from now. We could do this next Monday or maybe the Tuesday after that. I know a lot of I heard you guys saying a lot of your teachers are giving quizzes on Thursdays, which maybe nice for a lot of reasons. It's unless you have them like all on the same day. So that's why I kind of got Monday, Tuesday lined up here. We can change that too. Okay. Or we can do the kinematic quiz the week after. And so let's see, show of hands what you guys are thinking. All right, we'll try and narrow this down. Okay. First, let's see, do you guys want to do this next week or the week after, right? Okay. So how many of you guys want to do kinematic motion quiz about 1 week from now? About 1 week. All right, so I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, 18, that's the majority of the class, right? 18. All right, so between these 2 days, would you guys rather do Monday or Tuesday? All right, how many guys would rather do Monday, coming off the weekend, Monday? Is there one? All right, who wants to do Tuesday? Ooh, okay, that looks like a fair majority. All right, so I will go fix my plans and we'll aim for kinematic motion quiz that day. All right, so Tuesday, February 1st. Right? Oh, yeah. Is that really? Ah, you're right. You're right. That is the 31st. Yeah. All right. Thanks, Sharon. See that. So Monday was the 30th. Yeah, Monday was the 30th. All right. There we go. So let's go to that. Tuesday, January 31st. All right. We'll put this one again. All right. All right. So I'm also going to start breaking out AP practice exams. So notice this next week here. This maybe the second half of the week. If I have you guys doing this here and we're going over some of these. Or maybe I might possibly have to bump that to the week after. But I'm going to start getting you guys full AP exams, all the multiple choice questions to deal. Now, just a couple of years back, they bumped some of the units. So like anything from like I think like 2019 before, there's some questions about like electricity and waves and stuff. But we'll manage that. All right. So we can do that. All right. All right, so you guys good with the plan so far? All right. You guys got in your agendas. All right. AP classroom. There's one open. Got this tentative due date here. All right, and then Kinematic quiz coming up about next week. Right, so you guys got that in your agendas? All right, so let's go finish, pick up where we left off last week with these midterm solutions. Right, so we were looking at here. Yeah, let's just we'll knock out these two and then okay, go from there. So number 59, 59 and 60. You guys see a couple of graphs, right? You guys know you're going to see graphs all over the place. You might even have to draw these graphs yourselves, right? It's like in an upper key situation. Okay? We got here, even if you don't read any of the questions, this graph, just look at the axis. It's force versus distance, right? Force measured in newtons versus distance measured in meters. And this other graph is force in newtons versus time in milliseconds. Ooh, okay. So guys, whenever you see a force versus distance graph, you're probably going to get a question about what? Work. Yeah, work or energy, right? Because what property of that graph represents work or energy? The area. Right. Versus if you get force versus time, you're going to get a question about what? Momentum and impulse, right? Right? Like a change of momentum, which is also the area, it's the area, different axes. Okay, so you get, just by glancing at the graphs, like you kind of know what question's coming. Okay, so I got a rocket with this mass moving at the speed, right? And then they blast the boosters, blast the thrusters. Right, so we got this force, this many newtons for this particular distance. Ooh, right? Maybe that's kind of a weird way to do it, but whatever. That's what we got. Right? The question is, what's the final speed of the rocket? So, well, okay, so it's speeding up, right? So it's going faster. It's blasted in forward direction. How fast it's going to go? There's actually two ways you can do this, and the way I intend it is conservation of energy, right? Well, it's not really conservation because it's an open system, right? But sort of think about like with that framework, right? So it's more like this. It's an open system. That's true for the next one too, right? It's hey, so here. This is 59. Next one's 60. All right, there we go. Okay. Right, so we got sum of energy initial plus the work, which is like a change in energy, equals sum of energy final. Okay. This is straight from unit 4, right? Unit 4. Okay. I think actually AP asks more questions from unit 4, like this type of stuff, than any other unit. Okay. So what should you put in for this term right here? Rocket in deep space. Yeah, 1/2 mv squared, right? There's no MGH, there's no gravity around, there's no springs. Okay, so it's just some good motion, right? And then work is, well, that's the area of that graph, right? So it's like force times distance. Right? Now sometimes you get a variable force, like a triangle looking graph, right? And so, if you're in calculus, might say just say like the integral, something like that. Right? So that f dot b distance or something, right? But in this case, the rectangle, so I can just say that, okay? And that's 1/2 mv final squared, and this was initial, right? So there you go. That's what you had to come up with. So let's put in the numbers. We got 4,500 kilograms, 4,500 kilograms rocket. Okay. In this case, the math does not cancel out because it's going to matter. 1/2 4,500 kilograms. Okay. It was initially going at had 500 meters per second. Don't forget to square that. It's kinetic energy. Okay. And then got 5 million newtons, 200 meters. So 5 million newtons, 200 meters. Right, and then B final squared. Boom, just like that. Okay. Boom, boom, right. So we got 1/2 times 4,500 times 500 squared. Okay, so that's a crazy big number plus 5 times 10 to the 6 times 200. Another crazy big number, right? Then multiply this 2, divide this 4,500, and then take the square root. Right, I'll just do power 0.5 for a square root. Right. Anyway, cut through some algebra steps here. I'm getting 833 meters per second. Yeah, that's an answer choice, so we're good with that. Okay, you guys good there? Now, there was an alternate way you could have done this. You could have treated this whole thing as a unit 2 problem with forces, dynamics, acceleration. Okay, so you say, well, if I got this force acting on this mass, I could calculate the acceleration. And then I could go back to unit 1 right here. So it would have been this. Right? So step 1 would have been acceleration as a force acting on a mass. And step 2 would have been df squared equals v naught squared plus 2ax. And then that feeds in right there. Right? And then you can solve for it that way. It gets you the same answer. I went back and double checked this way too. I think the numbers I came up with, it's like ridiculous acceleration. So I don't know how realistic exactly that is, but in terms of the physics, it matches stuff. Okay. All right, that's good. All right, and then last one, baseball, which has this mass thrown at this speed towards the plate, and the batter hits it in the opposite direction. Okay, so careful about opposite direction because you guys know this is an impulse question, just from the graph, force versus time. But impulse momentum, that's a vector, so directions matter. Okay. What's the post-collision speed of the baseball away from the plate? Okay. So at number 60, this is also an open system consisting of only the baseball. Okay. So we're going to do sum of momentum before plus the impulse, the change of momentum, equals sum of momentum final. Okay. But you got to be careful with your negative signs, right? To tell someone about the direction of the baseball, which is changing, right? It was going to the left, now it's going to the right. So I got mv naught plus, if you like calculus, maybe you like this notation. T equals mv final, right? So this is just a notation for like the area of that triangle, right? Right. So got the baseball was 0.15 kilograms. Okay. Now it says a speed of 15 meters per second. But since I know the force is acting opposite that direction, I'll go ahead and tag the negative sign to that right there. So call it negative 15 meters per second. Area of a triangle, 1/2 base height at a base of 20 milliseconds. So would that be 20 over 1,000 seconds? Okay. Whoops, that was the time. Oops. Okay. And then the force was 500 newtons. I've got 500 newtons. So that I got this crosswise or multiplication is commuted different. Okay, and then 0.15 kilograms be final. Okay, so here's the initial momentum in the negative direction. Here's the change of momentum. Bam, hit by the bat. So it's going to hit off some speed. Okay. So 0.15 times negative 15 plus 1/2 times 20 on 1,000 times 500, all divided by mass of the baseball here. Okay, cut through some algebra. The final is 18.3 meters per second. Okay, that's a positive value. Okay, and then, okay, that looks like that. So I'm all good here. Okay, see you guys today. Okay, yeah, so all these questions were pretty fundamental. You could totally see any of these on an AP exam. Okay. I did want to do one lesson. Let's go back to the very first question. I mean, that was segue back into kinematic motion anyway, right? Okay. I wanted to draw a diagram to match, because I think went over verbally what parts of the graph match what was going on physically, but let's draw this out actually. Okay. So edge of the cliff, you throw a ball straight upward, some the initial, then right down this way, right? Okay. So basically straight up, straight down. We're treating this as linear motion, right? Straight up, straight down. Okay. Right. Now it clearly changes direction. Right. So okay, so velocity is -1 point, +1 point. So you got to pick a direction to be positive. If you call it down positive, which would match the graph because the slope is positive, so gravity is pulling in positive direction. Okay. Then the way you initially drew it was negative. Okay. And this little triangle right here represents some kind of displacement, right? This displacement right here, like this this delta x, right? That displacement is this little triangle, right? This big triangle is the distance from the peak all the way back to the valley floor, right? So delta x1, delta x2, right? There's the big triangle right there, right? And then the actual question was, what's the height of the cliff? Right. So one way to do that is, okay, well, that's x2 minus x1, or you could say the big triangle minus the little triangle on the graph tells you the height of the cliff, h. Okay. Or if you like, this trapezoid right here, it's the same thing, right? All right, guys, good. Did match up? All right. Any questions on this midterm? We're going to do stuff. Guys, good. All righty. All right, let's switch over and look at the AP's Unit 1 guide, right? Because I'll take you guys through that. You can see like exactly from AP's point of view what they want you to know. Right? No question about that. All right. Switch over here. 3, 2. All right. Oh, look at that. All right. So 12 to 18% of the questions are going to come from Unit 1. I mean, that's a pretty fair split, right? Like if you take, you guys got what, 7 topics? So 100% divided by 7, it's like 14, 15% somewhere in there, right? Which lands right in that window, right? Some topics are weighted a little bit more, some a little bit less, but this would be like about average representation. Right, there you go. All right. So Unit 1, kinematics. There we go. Unit 1, kinematic motion. All right. So, yeah. All right. Preparing for the AP exam. There's an experimental design question in the free response section that is worth 12 points. Students must be able to justify their selection of the kind of data needed to answer the question. Right. So that's where you see like we've got something we want to figure out, some experiment we want to set up. What tools do they have to use to say, oh, well, I would use the meter stick and the stopwatch, right? It's just a handful of tools that the same ones that you guys use in this class, right? When presented with experimental design question, students often do not know where to start. Students should be given scaffolding opportunities to determine the appropriate data needed to answer a scientific question. Okay, so it's just talking about like setting up labs and stuff, right? You guys have done like so many labs, right? For this particular section, let's see. Remember, you guys were rolling cars down the incline. You guys did graphs with x versus t, v versus t. You guys had speed gates. You guys did linearization of axes. You guys did one where you like dropped a ruler and had your friend try to catch it. You measure reaction time, calculate reaction time. We took the projectile launchers out. You guys did some projectiles. Those were some of the things we did. All right. Sample activities. All right. Oh, okay. So things we did. Okay. We're looking for enduring understanding. Okay. So topic 1.1, position, velocity, acceleration, kinematic motion. Right? All forces share certain common characteristics when considered by observers and inertial frame of reference. Right. So inertial frame of reference means it's a non-accelerating frame of reference. Right. 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 Essential knowledge. Observer in a frame, reference frame can describe the motion of the object using quantities like position, displacement, distance, velocity, speed, and acceleration. Okay. So when you see the equations pop up, AP usually does it in terms of like position, like X could be like some exact like coordinate. Usually when I do it in class, I'm referring to some kind of displacement, but if you want to distinguish between those two, sometimes you can do like delta X for displacement, right? Right. And distance, you guys know, is a scalar, whereas displacement's a vector quantity, right? Okay. right? Similar idea with the velocity versus speed, right? So speed is the scalar, velocity is the vector, right? Vector meaning direction matters. Displacement, velocity, and acceleration are all vector quantities. There you go. Displacement is a change in position. Velocity is a rate change of position with respect to time. Acceleration is a rate change of velocity with respect to time. Changes in each property are expressed by subtracting initial from final values. So there you go. So you can put that in equation form. Velocity is a rate change of position. Acceleration is a rate change of velocity. Choice of reference frame determines the direction and magnitude of each of these quantities. So kind of like deciding is up or down positive. So which way is gravity pulling? You know, what do you attach negative signs to? But also, suppose you're like in a plane moving at a constant velocity. Right? Now, guys, moving in a plane at a constant velocity, is that an inertial frame of reference? Yeah, because constant velocity, that's not accelerating, right? But then if you said like, how fast is something else moving? Well, that would be a different answer from if you were like standing on the ground, right? Or what if you're standing on the moon watching the Earth spin, right? So that's where like magnitudes can be different depending on your frame of reference, right? There are three fundamental interactions of forces in nature, right? We've got gravity force, electromagnetic force, and strong force. Okay. Right. In the past, I know they've always said four. They also include the weak force, right? All right, so you guys know what gravitational force is, right? It's like mass is gravitationally attracting, right? Now, if you get down to like graduate level physics, they might even say that that's not technically force. It's more like an artifact of like the warping of space-time, but we're going to treat it as a force, right? Mathematically, Newton's law, inverse square law, right? Electro. Oh, whoops. Okay. Okay. I see. They just combine two forces here, right? So electrostatic force versus a weak nuclear force. These are different things, but they're right. So electrostatic force is like anything like suppose you like pick up a pencil, right? There's atoms with electron fields between the pencil and your hand that's like pushing against each other, right? What about friction? What about like just pushing, pulling, friction, anything like that? Now, there's a couple of nuclear forces that you don't really care about for this class. The strong force and the weak force. That's actually what they're called. It just has to do with like holding the nucleus together and something with like radioactive decay or something. But just know they're there, and you don't really have to do anything with it. These fundamental forces determine the structure of objects and motion of objects. Right? Essential knowledge. Right? Continued. Right? Part E. In inertial reference frames, forces are detected by their influence on the motion, especially velocity of an object. So force, is a vector quantity, just like velocity is a vector quantity. Okay? I don't know why they're talking so much about forces here, because force is not even in any of these kinematic equations, right? Kinematic equation, all you care about is like displacement, velocity, acceleration, time. So, but whatever. It's more of a unit 2 concept, I would think, right? When multiple forces are exerted on an object, some of the forces referred to as the net force causes a change in motion of the object, right? Well, maybe this is kind of the crossover, right? So forces cause accelerations, right? Yeah, to me, like if I was crafting this document, I would put all this stuff in like unit 2, but whatever. Kinematic equations only apply to constant acceleration situations. Right? So you guys know rate change of displacement is velocity, rate change of velocity is acceleration. But that's usually where we stop, right? Like, we don't really have like a rate change of acceleration. Do you guys remember what that term is called?
Sure.
Yeah, jerk, right? Jerk, right? Unless maybe you consider like harmonic motions, like pendulums going back and forth, or mass on a spring. You could like take the rate change like forever and just get these sine and cosine graphs like forever, right? But just like a car speeding up, slowing down, we're assuming what's called uniform acceleration, right? Uniform acceleration. So like constant acceleration. Right? Circular motion and projectile motion are both included. Circular motion is further covered in unit 3. Yeah, circular motion is kind of divvied up, right? So there's 3 classic kinematic formulas here. You guys can see those posters back there, right? The green one and the yellow one right below it. Right, so there's like x equals v naught t plus f a t squared, and then the other 2 kinematic equations there. There's the rotational equivalence. So if you break out a turntable and start spinning it, merry-go-round type situation. And then circular motion also popped up in unit 3 with like centripetal force, right? Your mv squared over r. Okay, you guys are going to do the whole lab with the Plato canisters and pipe, right? And then circular motion popped up again in unit 7 because we had rotational dynamics, so we had to go back and look at that again. So rotational circular motion is kind of spread out over different units, right? Unit 1, unit 3, unit 7. Okay, but here you go. Here's the 3 classic kinematic formulas. So I write them a little bit differently. This is how they're listed on your AP equation bank. I think they're like the first 3 equations on your equation bank, right? Right at the very top. Okay, so we got V final equals V initial plus AT. Now they also, here, let me zoom in a little bit here. Oh yeah, that looks a lot better. Okay. They also throw on subscript X. Now this subscript X just refers to like the X direction, like the X axis, right? But you could swap that out with the Y axis or the Z axis. They're just saying along one particular axis, like a one direction, something like that. Okay. The second one is the one that I usually list first, which is here. I would do this. I would take this. See, the way they have it is final position equals initial position plus dot 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 dot. Right. The way I write it is if you take this x naught and subtract it over, you could call that displacement. Right? Like final minus initial position could be displacement, right? Right. And then I just go from there and say equals v naught t plus half at squared. Right. So initial velocity times time plus 1/2 acceleration times squared. Assume uniform acceleration, it all works out. Okay? You guys know graphically, this could be like a rectangle and a triangle on a v versus t graph, right? V versus t. Right? Okay. And then this final one, v final squared equals v initial squared plus 2ax, right? And then where I would say x for displacement, they went ahead and got even more granular with that. They said final minus initial position, but there you guys see that, right? They're doing like in terms of position for x. There you go. Right? All right, you guys good with those? Right. And really, hopefully you guys do have those memorized, even though you have them on your equation bank too. But I mean, you guys just use them so much for the past year, right? Right. For rotational motion, there are analogous quantities: angular position, angular velocity, angular acceleration. Oh, there you go. Right. Okay, they reverse the top 2, right? Because if you take this and this, all right, so swap the top 2, and that's more how I tend to write this, right? So theta could represent angular displacement. You can measure in degrees, but radians is better, right? Radians is better if you're using these equations, right? Okay. Omega, this curly W looking thing, is like angular velocity, like how fast something rotating. For example, the Earth makes 1 revolution every 24 hours. That could be a type of omega, right? But maybe you could quantify that in radians per second would be even better, right? And alpha, angular acceleration, is like the rate that you're speeding up or slowing down spinning. Okay? Could be radians per second squared, right? Radians per second per passing second that you're changing. Right? And time is still time, right? So t is still t. That's the only one that's still the same. Okay. Okay. And for each of these set of 3, I think the top 2 are somewhat intuitive, or you know, the third one of each line you can show with the system of equations. The top 2 you can derive it. The third one is also kind of closely related to conservation of energy, right? If you think about potential kinetic energy, you can it's like a step away from that too. And so this also includes situations where there is both radial and tangential acceleration. Right. So suppose you have a turntable spinning. Right? They didn't have to say acceleration. They could have said velocity too, like same idea, right? So here, if you have a turntable spinning, well, the entire turntable has one constant angular acceleration and one angular velocity, right? But depending on how far you are from the center, right, you have different angular velocities or different angular accelerations. And you guys know the connection is A equals alpha times R, right? Where R is your distance from the center, and V equals omega times R, right? So straight. Oh, and that's that poster right back there too, right? Right next to the that one, right? So it's like 4 over 1 down, right? Okay. All right. Okay, and then here's centripetal acceleration, which actually that came in more like in unit 3. That's really a unit 3 type thing, right? If you multiply both sides by mass, you get centripetal force equals mv squared over r, right? That's what you guys did for unit 3 lab, right? For uniform circular motion radius r, v is proportional to omega, right? Right, so right, okay, so if you're like twice as far from the center, you're going twice as fast in the linear sense, right? Like break out a radar gun kind of do. Okay. All right, if you have a time period rotation t, you can say the linear speed is right here. We got the circumference is 2 pi r, right? Right? So if you went that distance, notice I'm not saying displacement, I'm saying distance, right? That distance around on a turntable. And it took some time period t to make one rotation. Okay, so distance over time could be your speed, right? Like, and this would be tangential speed, right? Like linear tangential speed. Right? Ooh, boundary statement. AP Physics 2 has learning objectives under electric and magnetic forces, context interactions. All right. Rather than the mechanical systems introduced in Physics 1. Yeah, so if any of you guys take AP Physics 2 with Mr. Gentili, you'll do more, like a lot more electricity, magnetism, that sort of thing. Okay. All right, so we are. Topic 1-2, representations of motion. And I don't know why they put this here. It seems more like a unit 2 thing, but okay. Right. What causes accelerations? Well, it's a net force acting on a mass. Here's one way to set say net force, right? It's the sum of the forces. Right? Notice they have little arrows over the quantities, right? So that it means it's a vector, right? So if you have like opposite directions, you have to like subtract forces, right? Now force could be in 3 dimensions, so you have to think along each axis, right? AP will probably ask you guys like 1 or 2 dimensional questions, right? You might get a 2-dimensional question. Actually, one of your midterm questions was 2 dimensions. You guys remember flip back over here. Go back before the weekend. Like this right here, right? So like what's the tension in each string, tension in each rope holding this up, right? Well, that's forces in 2 dimensions. The forces sum to 0 horizontally, but they also sum to 0 vertically, right? You have to break them into components and then go back. So that could be right, essential knowledge. Linear motion of a system can be described by displacement, velocity, acceleration of its center of mass. Right? Right, so there you go. There's the 3 kinematic equations again. More essential knowledge. Acceleration is equal to the rate change of velocity. Right? That's actually the first way you guys were introduced to acceleration. So, well, it's the rate that you're changing your velocity, right? How fast are you speeding up or slowing down? This car goes 0 to 60 in 8 seconds, right? Velocity is equal to the rate change of position with respect to time, right? So how fast are you changing your position, right? The acceleration of the center of mass of the system is directly proportional to the force acting on it, right? Yeah, I think it's more of a unit 2 idea, but okay, sure. Right, that's Newton's second law of motion, right? Okay, and here's the other part of Newton's second law of motion. So A equals F over M. That's the equation version of that paragraph right there, right? Right, so A equals F over M, right? And that's a vector quantity, direction matters. Force and acceleration are both vectors. Acceleration is the same direction as the net force, right? If you have one object with like 3 different forces on it, you got to find the net force first, right? You might have to break things into components, yada, yada, right? And once you find the net force, well, that's also the direction that it's going to move. Right? It's going to accelerate, I should say, right? It's going to accelerate, right? The acceleration of center mass is equal to the rate change of the center, rate change of velocity with respect to time. I said that already. And the center mass is equal to, and the center of mass velocity is equal to the rate change of position with respect to time. We've got x, v, and t. X, v, and a all refer to center mass quantities. Okay, so yeah, back when you guys were learning this for the first time, we were treating objects as like point masses, right? So individual points. But as you guys got later on through the semester, said, well, like what if you have like a beam and it's being held by ropes at different locations, and you're trying to figure out what's the tension of this rope versus that rope. So then objects were like kind of spread out, right? So all these equations refer to really like the center mass point. Okay, so there's Newton's second law of motion there. There's the definition of velocity. There's the definition of acceleration. Okay, so you guys good there? Oh yeah. Okay. All right. Okay. I think that's it. I think it's the whole thing. All right. All right. Let's go look. Check these learning objectives too. All right. All right. So, sure, I didn't miss any of these. Okay. Express motion of an object using narrative, mathematical, and graphical representations. So mathematical is the 3 kinematic equations. Graphical, I mean, we did so many graphs, right? You guys did X versus T, V versus T, A versus T graphs. If you know one of those, you can kind of figure out what the other 2 look like. rates of change, areas. Right. And narrative, sometimes they'll have you like write out a paragraph where you spell out the words, like, right. Some FRQs like that. Design experimental investigation for the motion of an object, right? Well, you guys did a few, and then just pop up in the FRQs. Analyze experimental data, describe the motion of an object, express the results using narrative, mathematical, and graphical representations. You guys can do that, right? Write a paragraph, set up an equation, draw a graph, interpret graph. You guys can do all that. Okay. We got, okay, same thing there. Oh, okay, looks like it's just a repeat. Let's get those. All right, skip on down here. Use representations of center mass of an isolated two-object system to analyze the motion of a system qualitatively and semi-quantitatively. Right, okay, you guys can do that. All right, here, make predictions about the motion of a system based on the fact that acceleration is equal to the change of velocity per unit time. Velocity is equal to rate change of position first time. True. Create mathematical models to analyze graphical relationships for acceleration, velocity, position, center mass of a system, use them to calculate the properties of motion of center mass of the system, right? So like if I gave you a V versus T graph, you could look at that graph and say, oh, well, the area under V versus T tells me displacement. And the slope of V versus T tells me acceleration, right? You guys have done that so many times in here, right? Including on your midterm that we were just looking at too. All right, so there it is. There's the whole everything you need to know for Unit 1, which again should be about, there you go, about 1/7 of the entire AP exam, right? Yeah. Yeah, I will do that too. Let me pick it up.
Thank you.
Yeah. Yeah. I'll go ahead and do that for all the units. I'll post all the units to Google Classroom. Right, you guys have that. All right. Let's do here. All right, let's do this. And so I'm going to stay here.